All right. Greetings in the mighty name of our Lord Jesus Christ. Thank you for being here with me. All right. Really appreciate it. Last time we spoke about we're gonna do fluid 5. Last time we spoke about the basic concept, of fluid, and I think this chapter complements this one. So today we'll be looking at measurement of flow. As you see, it's the heading on my paper over there. I'm trying to work on the angle of this camera. Right. We'll be looking at the measurement of the flow. Measurement of the flow, meaning what's happening with measurement of the flow is that we are looking at the velocity most often. We're looking at the velocity. The most important thing that we'll be looking at is the velocity of them, is the velocity of the flow, meaning in fluid we can use air, we can use we're going to look at the velocity of air. Remember, air is part of gas, and gas can be flow, so and gas can be fluid, and fluid obviously they can flow. Anything that has an ability to flow, it's a fluid. And gas can flow. We're gonna look at it, and we're gonna look at fluid as in like water. We look at the water. We're gonna look at fluid as a oil. We're gonna work with oil, and fourthly we're gonna work with mercury. So you're going to deal with these four types of fluid movement, meaning we have to know, we know when we come into measurement, when we work on measurement, precision measurement, when we work on precision measurement, we know we have to know how to use vernier calipers, outside mics, all those measuring instruments, you can name them. So even in fluid, we do have measuring instrument to measure what? The flow. Let us name few. We're going to work with 3 of them, meaning the first is going to be pitot tube. We're going to work with pitot tube. This is the first. We're going to work with pitot tube. We're going to work with pitot tube. After working with pitot tube, our second one, this is the first one. I'm going to explain what a pitot tube is. And the second one, we're going to work with orifice on how we calculating the flow on an orifice. And the third one is a venturi tube. So we're going to work with these 3 types of measurement. So it means we have 3 types of measurement to measure fluid: pitot, orifice, and venturi tube. So when you talk about pitot tube mostly is used to measure velocity of fluid. All of them, in fact, it is used to measure the velocity of fluid, and they usually install it in the middle of the pipe. We're gonna go through it and see how we're calculating it. And when you talk about the orifices, we usually talk about there we're going to look at the contraction and the connection of the pipes and the tank. Usually it is used on a tank and a pipe where we have to reduce the diameter from a bigger container to the smaller one. So here we're going to have something called a sudden contraction, where we're going to talk about it. And when you talk about venturi tube, it is like a plate. Usually they use it as a plate. They use a venturi tube plate. It's like a plate that they put in the middle of the pipe, and whenever fluid comes, it has to pass through that small plate. That's where the velocity is being calculated. So it's going to be fun, amazing, and lovely to study these 3 things and to know how to calculate the velocity from each. So if we put our mindset that this chapter is all about calculating velocity, we're gonna get it right. All right, let us go straight to pitot tube. When we talk about pitot tube, I just want to draw a simple drawing here of a pipe. Let's assume we have a pipe like this, and it's cut here. Even here we have a pipe like this, it's cut over here. this is how they install a pilot tube. Pilot tube basically it's something that has a gauge here. Let me just use an arrow, then there'll be numbers over it like that. So there's a type of a fluid, we know inside the gauges they put something like a glycerin that is going to help the gauge to move, and it's a pipe that moves like this. Then it's a pipe that moves like this, and it has an opening here. So whenever the fluid enters through here, it's able to kick the gauge, and the gauge will read. So we know that pilot tube, it has to be fitted inside what? The pipe like this, as far as I just explained about it here. So here's going to be our pilot tube with a gauge. So whenever fluid comes through this direction, comes through this direction, it's gonna enter through here. When it enters through here, it's gonna go here. So it will push the gauge, and the gauge will read at what speed is this flow moves at. So we do know that we have different types of flow. We just explained from basic concept of what of a flow. We know that we have viscous flow, which is a laminar flow, and we have what? Turbulent flow. So pilot tube, when we install it in a turbulent flow, it has to be close to the surface of the area. And when we install it on a laminar, it has to be on the center. So that's the two things we just have to know. It's a food for thought, in fact. And what we have to look at right now, I need us to look at something called the recovery head. Recovery head. We'll be talking about the head as well. Recovery head. We'll be talking a lot about head in this module. Velocity and head are the most two important things that we'll be talking about. All right, let's look over here. If we say that a pilot tube, usually it is accompanied by a mercury manometer. It is always accompanied by mercury manometer. Let me draw a mercury manometer in this sketch. Our mercury manometer, it is sometimes drawing like this. They can sometimes put it like this, sometimes put it like this, sometimes put it like this, sometimes put it like this. Then it's going to be connected to the pilot tube like this. So our manometer, inside it has a liquid that moves. The liquid can be from maybe at this point, and it's going to fill is going to be filled over here, maybe until to this point. So this is the point of from this distance to this distance. We're going to call this a recovery head. Recovery head is always calculated on a manometer. It's always calculated on a mercury manometer. The more the velocity increases, the more this head, the more this fluid will go up like this. It means we're going to have a higher head, and the lesser the fluid comes in here, this reading will go up. Sometimes we might find out this one is gonna come somewhere over here, and this one comes here. So that's where the manometer works. The manometer only helps us to get what? The recovery head. So we now know about that. So one thing we have to know about the recovery head is that it converts a pressure, actually the pressure energy converted to EK, meaning kinetic energy, and we take the test. And after the test, our kinetic energy is now converted back to pressure energy. What do I mean? It means what I mean is that I'm going to explain it into mathematically. Here at the pilot tube, at the opening of pilot tube, we're going to have point, let me name it point 2. And from here on the pipe, at any point, you can name it point 1, meaning the flow here, it was at what? It was at a kinetic, it was at kinetic motion. It means it's a EK, meaning it was flowing, it was running. The water or whatever that we are using, oil, it was running up until it reaches this point of 2, where it has to stop and enter inside the pilot tube. Then at this point, we're going to name this point stagnation point. It means here it stops. So it means we have position 1, and we have what? We're going to say position 1 is the same as position 2. Position 2 is the same as position 2. You see, position 1 is the same as position 2. So we know that these are the same. How do we know that? I just explained that the recovery head says that pressure energy converted to EK, then we take measurement, and the pressure, the kinetic energy is now converted back to pressure energy. Let me explain. When we move here, the fluid here will move. It means we have EK. Then when it have EK, it's going to stop here. When the fluid stops at stagnation, it means we no longer have kinetic energy. Remember, kinetic energy is a dynamic. And when we talk about dynamic, we talk about motion. So it means here we're going to have we're no longer going to have motion. So what type of a pressure are we going to have there? Remember, conservation of energy says that energy cannot be what destroyed or created, but can be what transferred from one object to another. It means we always must have energy of something. When it stops, we're going to have a pressure energy. Now we know that pressure energy, kinetic energy is converted to pressure energy. The moment then it enters inside this, the fluid has to come inside and move. When the fluid starts moving, it's what we have EK inside the pilot tube. It means now we are converting back. We're converting back from EP to EK. Then it now enters through the pilot tube, and when it enters, it has to stop. When it stops, it kicks the indicator. Then the indicator starts reading. It means now we have what? A pressure energy. So the two energy complement one another to get what? The recovery head. All right, don't be too much confused with that. What I'm just trying to say, I was trying to explain Bernoulli's equation. Remember, Bernoulli says that all total energy, kinetic, potential, and pressure energies will remain the same throughout the system unless there's an external force act upon. That's what Bernoulli is saying. So if that is the case, we're still going to use our formula. We're still going to use our beautiful formula of Bernoulli, where we say Z1 plus P1 PG plus V1 squared divided by 2G equals to Z2 plus P2 over rho G plus V2 squared over 2G. We're still going to use the same formula of Bernoulli. It means that what was happening at position 1 is this. We have height, which we know at this point, height is going to be 0. At this point and this point, they are on the same level, right? Then we know our height is 0. At this point, we don't have kinetic. We don't need a potential energy. We know the potential energy is 0 both sides because the pipe was on the same length. It means potential energy cannot be affected. Let us assume if our pipe was staying at this position. It means our dentam line is going to be here, which on the previous chapter I taught you about dentam line. Then this will go up and we're going to have height here. It means at position 1 our fluid was at 0. It means you're going to put 0. Here at Z2, you're going to put this height from here to the position where the pilot tube is being installed. Can you see that? Then you're going to put it over here. That's where we're going to say that potential energy is being applied because of distance. Remember, when the fluid flows up, the velocity will be reduced because of what? The potential energy. Potential energy will take place. But when it stays straight, it can flow, or when it bends down, it has more advantage of flowing because of the gravitational force, right? Then we look at pressure. Pressure here will obviously going to be considered. We're going to have P1 here over PG. Then we're going to have velocity. Are we going to have velocity here? Yes, we're going to have V1 here. Then we say V1 is 2G. Here we're not going to have this, but we're going to have pressure at 2 because it is converted. Then are we going to have velocity here? No, we can't have velocity because it's at stagnation point. Then we say it's 0. So the velocity there is 0 because it's at stagnation point. So what do we have? We have pressure at 1, we have pressure at 2. It means we have pressure here and we have pressure here. We have velocity at 1, but we don't have velocity at 2. So it means our final equation, let me write it with a red pen over here. our final equation is going to be P1 into PG, rho G, and V1 squared over 2G equals to P2 rho G. You see? Then it means we have pressure 1 and pressure 2, and we have this. Then we can make our mathematical combinations where we say V1 squared into 2G equals to P1 minus P2 into rho G. Then we have this equation from this statement of conservation of energy. So we have this equation, then we know this equation. This equation is going to be crucial throughout our chapter. We're going to use it a lot. All right. Then, if that is the case, I need us to understand something about, I remember I told you that the purpose is to understand the velocity, is to measure velocity, right? Another formula that I need you to know and keep on mind is this. This is the formula I need you to know. The formula is velocity equals to C into 2 height, right? Let me confirm something with you. Okay, this is the velocity we're going to have. We're going to have that that equation. That one is very crucial. We're always going to use it all the time, Then this C, this V over here, it is called velocity of the flow, and this C, they usually call it a constant number. They just call it a constant number, and we're always going to be given it in ratio. Maybe it's going to be 0.92, 0.86. Then this 2 we know is 2. Then G is it's a gravitational acceleration is 9.81. Then height, it is the height we get